again, Trig. Welcome to Q4, week 4. We're moving on this week away from matrices and on to something that I really enjoy called conic sections. So, we're going to break down what this is, why we care, do a whole lot of vocabulary, because we're starting a whole brand new thing. There's a whole lot of vocabulary for us to learn, and do some math. So, a conic section. The first thing I notice is I always look at the title, conic sections. Conic reminds me of the word cone. And then section, usually when we section something up, we're like cutting it into pieces. So we are taking a cone and cutting it into pieces. So conic refers to cones. Sectioning something refers to cutting it into pieces. So this whole entire unit is going to be all about the different things that we can make when we cut cones into pieces. So first, we got to talk about how do we get a cone in the first place. So the way we create a cone is kind of like this. Well, let's imagine we have two non-perpendicular, non-parallel lines that intersect at a point V. So if I've got this line right here, and then another line that's going to intersect through this point, but it's not perpendicular or parallel, this point V. If we fix one of these lines, we're going to fix this line right here and call this the axis. We're going to say this one stays in one place. This is the axis. If we think about like the Earth's axis, that's the point that it rotates around. So we're going to make this other one rotate around in 3 dimensions. So if I take this blue, imagine in your head, if I take this blue line, spin it in a circle, this black line is going to kind of spin around, and it's going to create 2 cones that look kind of like this. So it's got a cone at the top and a cone at the bottom. That's a very crude representation. So we call the blue line the axis. This black and red line are the same line. They're just rotated to different places in space. We call this line right here the generator. So the axis tells us where we're rotating around. The other line is the one that actually creates the cone in space. So then each of these cones are right circular cones. So this creates 2 right circular cones. So what that means, the right angle refers to the axis and the base of the cone make 90-degree angles. If I could write a D the correct way. So the axis and the base make a 90-degree angle with each other. Need a little more space. And then circular refers to the shape of the base. So I could have a right square pyramid, which wouldn't be a cone. If it's going to be a cone, usually it's a circular base. Makes sense. Another vocabulary word. If you notice, this is actually like 2 separate cones. It's kind of divided right here. So we call each of these cones a nap. So this is the upper nap. And this is the lower nap. So that's how we get a cone. Now we gotta shift and move on to conic sections. So a conic section is a cross section of a cone. It's like we take the double cone diagram and intersect it with a plane in different angles. So there are three basic conic sections. A parabola, an ellipse, and a hyperbola. So how we create each one of these depends on how we intersect this double cone diagram with a plane. So let's look at some pictures, because pictures are going to help a lot with this stuff. Alright, so let's take a look at each one of these. So you're going to want to draw each of these in your notes. So the first one is not one we wrote down, circle. So if you take a look at this, the way we create a circle is by intersecting one of the cones with a plane. And you can see this right here. That is telling you there's an angle between the axis and the plane. So to make a circle, that's a perfect 90-degree angle. So a circle can be created just by having a perpendicular plane to the axis. So let's look at the next one. So an ellipse happens when I have one cone intersected and this angle right here, again, the angle between the axis and the plane is not 90 degrees. It can be greater than 90, less than 90, but it needs to only intersect one. It can't be 180 degrees or parallel. To the axis either. If it's parallel, that'll be something completely different. So an ellipse looks kind of like an oval. It is not circular. It's like a stretched out circle. We'll get more into what exactly that looks like in just a little bit. So let's look at the next one. This one is a parabola. So you can see the difference between the parabola and the ellipse is the parabola goes through the base of one of the cones. So again, it intersects one cone and the base. So if I slide back over to the ellipse, we can see the ellipse goes all the way through the cone, doesn't intersect the base at all. The parabola goes through the base. So you can see this is the parabola and it kind of goes through the base. Remember, planes go on forever. They don't stop, just like lines go on forever and don't stop. So really this parabola doesn't just stop right here at the base. It would keep on going in that same direction. And then the last basic one is the hyperbola. So you can see the hyperbola, now we have the plane is intersecting both of the cones. It's at an angle of some kind with that axis, and it goes through both of the cones and goes through the base of both of the cones. The hyperbola has to go through both of the cones. If it doesn't go through both, it's not a hyperbola. What is it? It's a parabola. So there's a couple other basic things that we could do with these as we're intersecting them. Like if I wanted to slide this plane for this circle all the way up and have the plane go right through this point right here where the cones intersect, I would have a point, just a point, because it would only be the point of the cones that intersect. I could do like the plane tangent to the cones, so it would just be touching each of these cones in one line. So I could have a plane that touches it and it would just give me a straight line. I could go perfectly straight through and get back to our intersecting lines like we used to generate the cone, but those we're not going to get as much into. So we're going to start talking more about parabolas, ellipses, and hyperbolas. And all of these we're going to relate back to this basic one, the circle. Okay, so let's talk about some definitions. What exactly are these things? How do we define each of these specifically? Before we get into some more specific definitions, I just want to show you one more diagram kind of relating all of these to each other. So remember, the one thing though is this hyperbola. There's actually another part of it up above. So the hyperbola has two pieces to it. Everything else has just one piece. And we can see how they are similar to each other and related to each other. There are some other conic sections known as degenerate conic sections, but they are atypical and lack some of the features usually associated with our basic ones, and we are not going to talk about them yet, but we will get there. Alright, so conic sections can be defined algebraically as the graphs of second degree also known as quadratic equations in two variables. So that means their equations are going to have the form ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0, where a, b, and c are not all 0. So you can have one of them 0, but they can't all be 0. Okay, so let's look at the definition of a parabola. So we've seen parabolas before. So a parabola is the set of all points in a plane equidistant equal distances from a specific line called the directrix and a specific point called the focus. In the plane. So parabola has two things, a directrix and a focus. Okay, so what does this look like? Let's draw a picture. So here we have an example of a parabola. It's in blue. You can see the axis of symmetry is our y-axis. This parabola's vertex is set up above the x-axis. So we can see the focus and the directrix are two new things that we want to take a look at. The focus is this point right here. So the focus works in conjunction with the directrix, which is this green line, to tell us where the parabola is in space. This defines where the parabola lives. So any point that you can put on the parabola will be the same distance from both the focus and the directrix. So I could pick any point. If I pick the vertex, this distance here and this distance here are going to be the same. I could pick a point way up here, measure the distance from that point to the focus, measure the distance to the directrix, and it will be the same. If you notice, my distance to the directrix is going to be perpendicular. That's going to be the shortest distance. So the distance from the parabola to the focus isn't going to be an angle because the focus is a point and not a line, so you can't make an angle between the two. But your angle right here between the point and the directrix will always be a 90-degree angle. So this one is 90, this one is 90, this one is 90. So the really cool thing about conic sections is that these all represent the paths of nature. Any free-moving object in a gravitational field follows the path of a conic section. We've probably in the past, hopefully Algebra 2, talked about parabolas, and that is like the shape of something that's being thrown up in the air. If it's an upside down parabola, that opens down. Something that's thrown up in the air and gravity pulls it back down. Shooting a rocket off into space, launching anything. These are all parabolas. As you see the word focus, some of these will also help us with things like lenses. So focus, directrix, focal width, these are all words that we associate with like optics, lenses, reflections of things. So let's talk about some basic things that we need to know about parabolas. So parabolas with vertex 0, 0, those are the easiest ones to work with. So, standard equation. Two different versions. So, we are not worried about things being functions and passing the vertical line test. So, standard equations, we've got two versions. We've got x squared equals 4py, and we've got y squared equals 4px. So, this one on the left opens up or down. This one on the right opens right or left. So the y here in the front tells us that it's going to be opening left or right. The x here, x squared, tells us it's going to be opening up or down. So these are great because if I'm trying to find the focus is just 0p for my up and down version. The focus for my left and right is going to be p0. And you can find that p here in your equation. So you notice that there's a 4 in front of the p. So if you have some number in front of a y or an x that's not squared, you can divide it by 4 to find out what that p value would be. So this is the focus. The formula for the directrix. Y equals negative p, or x equals the opposite of p. Opposite and negative, same idea. The axis of symmetry. For our up and down one, it is just the y-axis. For the left and right one, it is the x-axis. This is only true because the vertex of this is 0, 0. Okay, focal length. For both of these is p. Focal width. Is going to be the absolute value of 4p for both of these. So if you know the formula, you can now find all of these cool things. That's all cool, Miss Calgill, but we don't usually have things that have just so simple as a vertex of 0, 0. You are correct. So let's look at what all this looks like for parabolas with any other vertex. So, parabolas with vertex h, k. So, your standard equation. Is going to be x minus h squared equals 4p times y minus k. So this is your up or down. We're going to do all of this one first, and then we'll do each of these for the left or right. So what is the focus? So the focus is going to be this point, h, comma, k plus p. the directrix is the line represented by the equation y equals k minus p. The axis is going to be x equals h. Focal length hasn't changed, that's just p. Focal width hasn't changed, that's the absolute value of 4p. Alright, let's look at what each of these would be for our left and right facing parabolas. So our standard formula for the left and right facing is going to be basically our x's and y's kind of change places. Y minus k squared equals 4p times x minus h. So you can see the whole entire thing in parentheses switches places on these. Makes sense because the x and the h and the k and the y are coordinates and that are related to the x and y values. So this one goes left or right. So what is the coordinates for the focus of this one? It's going to be h plus p, comma, k. What is the directrix? So the line, the formula for the line of the directrix is going to be x equals h minus p. The axis is going to be y equals k. And our focal length again is p, and our focal width is the absolute value of 4p. Okay, let's look at an example of finding an equation of a parabola. Alright, so find the standard form of the equation for the parabola with vertex (3, 4) and focus 5, 4. So we're going to take what we just wrote down and see if we can figure out what is going on with this parabola. So one thing that I do sometimes is I will just think about graphing it real quick and think, okay, my vertex is at 3. 1, 2, 3, 4. 1, 2, 3. Here's my vertex. And my focus is 5, 4. So that tells me this is going to open to the right. So I'm going to be using the stuff that opens to the right or the left. So if you're stuck on where to start, plot your vertex and your focus, and that will help you know if you're going to be using the standard equation for up, down, or for left, right. The other thing this will help me figure out is the axis. So the axis of the parabola is the line that passes through both of these points. So if I look here, this is going to be my axis of symmetry. And this axis of symmetry is the line y equals 4. So that tells me the form of the standard equation I need to use is this one. Y minus k squared equals 4p times x minus h. So now we need to figure out where all these different variables come from. So the vertex has the coordinates hk. So that means h equals 3, k equals 4. So now we need to look at the focal length. So the focal length is the distance right between the vertex and the focus. So I can take my coordinates, and the distance from the vertex to the focus is 5 minus 3. I'm doing that because it's not always as easy to count and see that this is 2. But you can always take your coordinates. We know this is 3, 4, and this is 5, 4. And you can do your distance formula because it's not always going to be so easy. So we can see that the focal length is 2. 2 is p. So we also need to know 4p right here. So 4 times p, 2 times 4 is 8. So the equation that we are looking for is going to look like this. Y minus k is 4. Y minus k, so y minus 4 squared equals, instead of 4p, I've got 4 times 2, so I've got 8 times x minus h. H is 3. And that is the final form that I'm looking for, the standard form of the equation for this parabola. So another thing we can do with this is we can take an equation for a parabola that's not in standard form, put it in standard form, and then we can find our values for p, h, k, and that will tell us the information that we need to know about the specific parabola. So I'm going to give you some problems where I ask you to find the vertex, focus, directrix, and focal width of a parabola. Should be able to do that. If not, let me know. Send me an email. And we will see each other soon on Zoom. This was a long one. So when we see each other again next, we will talk about some of the uses of parabolas. So there's some really cool uses like radio telescopes, reflectors, lenses, and we'll get into some of those really cool things. And then we'll get into some more of that when we talk about ellipses and hyperbolas. And there's some really cool, strange things that happen.